welcome back to Chem 121. It is Tuesday of week 8, which means that we're getting very close to being done with all of this. Only 2 more weeks after this, then we have another exam and then a final, and my window just blew the curtain over the fan. Give me just a second, I have to fix that. Sorry, I have a fan moving air out of my window, and if the curtain covers it, then there's no airflow at all in here, and it gets freezing cold. Alright, let's see here. What are we doing? So quiz number 6 is due tonight. Excuse me. It is open until midnight tomorrow. Or sorry, I should say 11:59 p.m. on Wednesday, to be more precise. Make sure you get that in by the deadline. I am grading lab number 3. I almost have all of the stuff done and graded for all my classes, and then I'm going to upload that hopefully tonight, if not relatively soon. And then I realize that I do still have some NQA stuff that people have turned in, and I just haven't had a chance to get to. I will get to that forthcoming, hopefully. Yeah. So we're going to keep doing Chapter 7. So we're going to talk about state changes today. We're going to discuss what it means to have a liquid boil. And then the last part of the chapter is going to be the most important part. So we might actually finish this today if we... I don't know. I mean, it depends on how many questions there are. So, all right. So without further ado, on the screen here, I'm going to zoom this in so that you can see it. These are different phase changes that can occur when energy is either added or removed with regards to a system. Now, a system we're going to define as whatever it is that we are looking at that we care about. So, for instance, if I had like a glass full of water, the water would be the system. And we would designate it as a liquid because water is a liquid at room temperature. If I removed energy from the water, for example, I put it into a freezer, then it would turn into a solid. But if I heated the water, then it would turn into a gas. Now, all of these phase changes require energy to be manipulated in some way. And unfortunately, to write on this, I have to zoom out here. All the ones on the outside here. So this one, and this one. These processes all require energy. Now, the ones on the inside all result when you are removing energy. So energy is removed from the system. Oh, that's not what I meant to do. Sorry. There we go. And so now we can read what these actually are. So, since adding energy and removing energy are the opposite of each other, there are 2 different processes, and we give them different names. So, going from solid to liquid, we call that melting. But if I return from liquid to solid, we call that freezing. And you're probably familiar with most of these. Going from liquid to gas is called evaporation. You may also hear the term boiling. The reverse process, gas to liquid, is condensation. And then finally, there is a mechanism by which you can go from solid directly to the gas state where you don't enter the liquid state. A solid turning directly into a gas is called sublimation, and a gas turning into a solid is called deposition. Solid to gas is pretty rare. There are certain conditions and such as various temperatures and pressures that need to be met in order for sublimation to occur. but it changes depending on the substance you're looking at. So, for example, a common object that you've probably seen undergo sublimation would be dry ice. So dry ice is solid CO2. When solid CO2 sublimes, it doesn't enter the liquid state. In fact, if it leaves any puddles of liquid behind, that is actually condensed water. That was water vapor from the air. Liquid CO2 can't exist at room temperature and atmospheric pressure. You need to pressurize it a lot more for it to be a liquid. Another example of something subliming that I can think of would be if you put your laundry out on the clothesline to dry, but you live in, like, say, Alaska, and it's below freezing. All the water that is in your laundry will then freeze, but the frozen water, or ice, will eventually evaporate away. In fact, you can apply this sort of process to various things, and it's called freeze drying. You've probably heard of something being freeze dried. It doesn't get soggy this way, right? It's got ice in it, but then you evaporate the ice away by letting it sublime. The other process, gas to solid, is much more rare, as far as I'm concerned, and as far as any observations that I can make. We make things like mirrors using sublimation and deposition. So you turn, like, say, aluminum or silver or whatever into a very fine gas that then then deposits over a surface, which makes it a mirror. That's obviously not something that you're going to run into on an everyday basis. But yeah, so those are those states. The other ones are common enough. Now over here, I have indicated some energy changes. We're going to assign terms to these changes. So the first term that we're going to call endothermic is any change that requires us to input energy. In other words, if energy was added, that process is endothermic. So what are the endothermic processes? They would be melting, they would be boiling or evaporation, and they would be sublimation. Because all of those require you to add energy. Now, what about if you remove energy? If energy is removed or leaves the system, we call that exothermic. Now, you may have heard these prefixes before, endo and exo. Endo means in, and exo means out. For example, you have an endoskeleton. Your skeleton is inside your body. Some creatures, like maybe like a turtle, for example, have an exoskeleton. So endo and exo just mean in and out. Where does the energy go? Now, how do you perceive these changes of state? So for instance, let's suppose that you put your hand, so this is going to be our hand here. So here's our thumb. There we go. Something like that. I realize this, right, so now you can't unsee this. It looks kind of like a nose. But anyway, there's our hand. We're going to put it on a surface. If the surface is hot, where does the energy go? For example, let's suppose that, like, this is a stove. You're a kid and you're touching the hot stove. And you're about to regret all of your choices because the energy goes into your hand. And you feel that as hot, right? So when you feel the sensation of hot, into your hand. Energy flows into your hand. And what that means is that the object lost that energy. And so we would call this exothermic for the system. The system being the object that you're touching. So we perceive exothermic as hot. The energy is leaving the object, and it can cause a burn. Now, what happens if you do the opposite process? So let's say that the object is instead, if I could click this thing, cold. Where does the energy go now? Well, in this case, the energy leaves you and enters the cold object. And so now what happens is that when you feel cold, we'll just erase all these things here. When you feel cold, the energy is flowing out of your hand and into the object. So when you feel the sensation of cold, the energy leaves your hand. It is absorbed by the object, which we call endothermic. And again, this is relative to the system, which is the object that you are touching. So hot means exothermic energy is entering your hand, it's leaving the system. Cold means endothermic energy is leaving your hand and entering the system. Now, these are, again, relative to what you define as the system. If we defined, in this example right here as shown, if the hand is the system, then what process is this? Well, the energy is leaving the hand. And so we would actually define it as exothermic. So just be mindful of what you are defining as the system. In most cases, it's pretty obvious. It's going to be the thing you're examining. But from the perspective of the sensor or the environment or whatever is around it, the term flips. Because instead of losing energy, it's gaining energy, or vice versa. So just be mindful of that. All right. Now, we're going to focus particularly on the liquid to gas transition phase here. The reason that we're going to focus on this is because this process doesn't necessarily happen at a temperature. This process happens all the time. If you spill water on your countertop, like say you're doing dishes and you splash some water on the counter, that water isn't just there forever until you clean it up. What will end up happening to that water is it'll eventually just disappear, right? It will slowly begin to evaporate. The process of any liquid becoming a gas or vapor is called evaporation. Now, you'll notice that we use the term vapor here. What is a vapor? A vapor is not something that you say if you're like 1950s and shocked, like, oh, I have the vapors or whatever. No, a vapor, I have the wrong pen selected. A gas that exists at the temperature that it normally should be a liquid or a solid. So, for instance, when you heat water over 100 degrees Celsius, it turns into a gas. We call it steam. But water vapor is any water that is in the gaseous phase at a temperature below that temperature. So if you are going outside in, say, Florida, and you go, "Oh wow, it's so humid here. There's so much water vapor." What you're experiencing is water vapor. You are not experiencing what we would technically call gaseous water. We would call it water vapor because the water vapor is at a temperature below that of boiling. If you are boiling water over like a pot or like a stove and you have the water in the pot and you like take the lid off of it and some steam brushes against your hand and it's really hot, that would be gaseous water because it's at 100 degrees Celsius. All right. Now, water vapor is all around us. In fact, if you take a deep breath, you're breathing in water vapor, and more importantly, you're also exhaling water vapor. The air around you can have a certain amount of water vapor in it, and depending on how much that is, it will feel muggy and humid, or it will feel very, very dry. Or maybe it'll feel just right, depending on where you are and what your preferences are. If you grew up in the desert, you probably are used to just it being dry atmosphere. If you grew up in, I don't know, around the Gulf of Mexico, like Louisiana or Mississippi or whatever, you're used to muggy. You're used to everything just being sweltering and gross. You can tell where I grew up. It was not 100% humidity. Now, the process by which this happens does create a vapor, which acts as a gas. So here I have my liquid that hasn't evaporated yet, and when we allow it to evaporate, some of it will enter the liquid phase, and it will bounce around off of containers and stuff like that. And when it does this, it exerts a pressure, because those molecules are bouncing around on the container walls. Now, what does this mean? Well, if it has a pressure, we can assign it a value in ATM or torr or whatever. And so we're going to call this vapor pressure. All liquids have a vapor pressure. The vapor pressure is simply how much force that particular liquid contributes from its vapor. And you can see in the diagram here that before we have let anything evaporate, our little manometer here, which is this mercury column, is level on both sides. But over here, once we allow evaporation to occur, it will fill the entire container and then push against the mercury to create a difference in pressure. This is the premise by which a barometer works. A manometer is a tube that has two open ends. A barometer is a tube that only has one open end, and it's the end that points towards the atmosphere. The atmosphere pushes down on it, which pushes the column of mercury up into a tube, and so you can measure its pressure that way. Sorry, I had to cough there. I'm congested today. I don't know if it's allergies or just cat dander or what. So I apologize if I'm drinking a lot of water, so that my throat isn't scratchy. All right. What's going on in our liquid here, though? Now, as things evaporate, they won't continue to just evaporate. So the whole thing won't just evaporate out, and so it's all into the gas phase. Because what eventually happens is as molecules enter the vapor, up here, they can bounce all over the place. But one of the directions they could bounce is like this. If the molecules bounce around and then crash into the surface of the liquid, they re-enter the liquid phase, and therefore would be a liquid. Now, at some point, you are going to saturate the gas phase such that virtually no more gas molecules can be produced. No more vapor can be produced. And the reason for that is, for every molecule that escapes and enters the vapor phase, on occasion, molecules will return to the liquid phase. You can think of this as like, I don't know, some sort of venue or something for like, I don't know, a concert or whatever where people are entering and exiting at the same speed. For instance, maybe it's between shows, and so all of the audience that's in there is departing while the new people who just paid for the tickets to the next show are coming in. And so everybody exits out the bottom exit, but everybody's coming in out the top exit. So I guess that would look like this. So here's all my people outside. And so they're all leaving out here. Oh, crap. Hold on. This pen, I swear. There we go. But at the same time, I have people coming inside to replace them. And at any given moment, the amount of people inside is the same. For every person that leaves, another one enters. For the vapor phase, it's more or less like this once you have enough molecules up there. For every molecule that enters the vapor phase, another one leaves. And so the amount remains constant. When you reach this point, this is called equilibrium. We're going to talk about equilibrium more later on. But equilibrium provides a maximum vapor pressure for a given temperature. At a given temperature, molecules are only able to enter the vapor phase to some degree. Once there are enough molecules in the vapor phase, they start to condense back into the liquid phase. The whole time molecules are evaporating, but also at the whole time molecules are condensing. And eventually that equalizes, and you just have the same number of molecules in both phases over time. However many molecules are in the vapor phase, that's just how many there are. That pressure that we get to at equilibrium is our vapor pressure. Now, what determines whether something has a high vapor pressure or a low vapor pressure? That's going to depend on how our molecules in the solution, or in the liquid down here, interact with each other. I should underline the how there. So, for example, let's suppose that I have a bunch of molecules in my liquid right here. So this is my liquid. These molecules are very weakly attracted to each other. So I'm going to write some very nebulous dotted lines here. If this molecule suddenly goes off in this direction, these other molecules aren't going to follow it because the attraction is very weak. So therefore, the molecules can just escape into the vapor phase whenever they want to. But what if I had, for the same collection of molecules over here, what if I had much stronger interactions? Then when this one tries to move, all the rest of these molecules kind of get tugged along with it. And that might be too much for our liquid to escape to the vapor phase. And so the molecule just sorts of flutters about or moves all over, and the other molecules all chase after it. An example of this would be if you were trying to get up and leave the classroom, and in one case you did it with nobody else in the room, so it's very easy to leave. And then in the other case, you did it, but the room was jam-packed with people, like complete wall-to-wall people. And you're sitting in the middle of the classroom, and you're like, well, I want to leave now. But you're completely surrounded by virtually a mosh pit of people. You're not connected to those people in any way, but they do obstruct your ability to get to the door. So depending on the circumstances and conditions of liquid molecules and how strongly they interact with each other, they may or may not be able to enter the vapor phase. The conclusion that we're going to draw here is that if you have molecules that interact with each other strongly, the vapor pressure will be lower. For the reasons that we mentioned. If the interactions are really strong, it's very difficult for this to happen. It's very hard for molecules to escape to the vapor phase. On the other hand, if you have weak interactions, your molecules aren't attracted to each other, and they can easily evaporate. Now, what are these interactions? We're going to talk about that in the next section. Now, when does a liquid boil? We're going to have to go to this screen to talk about that. Let me put this on here. There you go. All right. How do liquids boil? Let's draw a little diagram to show what's going on here. So, I have a container, and that container has water in it, we'll say. And here's my water molecules inside the liquid phase. And they can move in any direction that they want to. And maybe one of those directions is up. So, I might have some molecules that have entered the vapor phase. So this would be my water vapor. I'm Canadian, so I put a U in every word. So that would be our water vapor. Now, if I leave my container like this, eventually everything will just evaporate away. But the solution, or the water itself, will not completely evaporate immediately. It takes a very long time. Now, let's suppose that I heated this up with, say, like the burner on our stove. As I do that, my molecules move faster and faster and faster. And more of these molecules will enter the vapor phase. And thus, the pressure of the water vapor will go up. Now, what is holding my molecules into the liquid phase in the first place? There must be some force that's holding all of the molecules together as a liquid. Or otherwise, they would just boil away and evaporate on their own. I wouldn't have to heat them up, right? So there's the attractive force between all my molecules, but there's also the pressure of the atmosphere pushing down onto the liquid. And while some molecules can escape, those molecules don't have enough force to push against the atmosphere. So here's our water vapor. It's pushing against it. But not enough, because there just isn't enough vapor. As I heat this up, the amount of water vapor increases. And if I can heat the water until the pressure of the water vapor is equal to that of the atmosphere, then the result is that we observe boiling. So boiling occurs when a liquid has enough vapor pressure to equal the atmospheric pressure. By heating stuff up, we can increase its vapor pressure, which is why we heat things until they start to boil. You can do this with any pure liquid. Obviously, water is the most common one because we boil water all the time for cooking. Sometimes we boil it so that we can purify it and then drink it. So maybe you're like out in the wilderness and you have to survive. You need water, but you can't just drink water out of a lake or a river because it could be contaminated with bacteria or stuff. So you boil the water, and then it's safe to consume. But the process of boiling requires us to heat the water such that the vapor pressure equals or exceeds that of atmospheric pressure. Once that happens, the water can basically push against the atmosphere and push it away. And thus all of the liquid water then becomes gaseous water. Alright, so that's how we get boiling. We're going to call the boiling point of any liquid the temperature at which the vapor pressure of the liquid is equal to atmospheric pressure. Now, interestingly, this has consequences for you if you live in a particular area. So you might remember this diagram that we drew when we started talking about atmospheric pressure and stuff like that. So here we'll put the atmosphere way up here. If you live over at sea level, the pressure that you feel is equal to 1 atmosphere, and the boiling point of water is what you'd expect, because it needs to resist 1 atmosphere of pressure and get a vapor pressure equal to that before it boils. But what if you live in Denver? I'm just going to make up a number here, but in Denver, the vapor pressure needed is less than this. So when you boil water, it boils at a lower temperature. In fact, if you've looked on the directions for something that requires you to boil water, you may have seen something that says high altitude cooking instructions. And generally what they do is they tell you to cook it for longer. The reason being, water boils at a lower temperature at higher altitude. That is because there is less atmosphere above you at higher altitude. So you need to make less water vapor, and the vapor pressure that you need to achieve is reduced in order to boil. In fact, what would happen if I could say, do this? So let's say, here's my container of water. I have water in here. Remember what we did with the gases, where we said, oh, well, I'm going to put it in a vacuum chamber and watch the effects of the balloon. What if I did something like this, where I removed the air around it? What would happen as I did this? Well, let's see. I mean, that's what YouTube's for, right? So let me find... Yeah, this is the video I want. Okay. Is this the video I want? We'll show it anyway. This looks pretty similar to what I was expecting. All right. So here we have a sample of water. And you can see that the water is at room temperature. What we're going to do is we're going to put this in a little vacuum tube, and we're going to remove the air from it. And we're going to see what happens. Now, I don't exactly know when this gets started here. But we'll skip forward. Oh, that's actually starting pretty quickly. Okay. All right. So we're removing the water, or the atmosphere around the water. And you can see that at the surface, it's starting to bubble. It looks like it's trying to boil. Now, I have not provided any heat here because I didn't make this video. But the person who's doing this experiment, there's no heat added. This water is still at room temperature. And as you remove all of the atmosphere from there, it starts to boil. Now, as soon as you reintroduce the atmosphere, it stops boiling. And you can see that the temperature is still 20 degrees Celsius. So you can actually boil things at room temperature if you remove... Oops, that's the music I'm playing. If you remove all of the atmosphere around it. So the atmosphere governs how much vapor pressure you need to induce boiling. And in order to get to that vapor pressure, we can heat up our liquid. So we can apply both the effects of pressure and temperature. So that's why we played with both of these, gases and also we talked about all those things about gases earlier in the chapter. All right, so here's some practice problems that I want you to try. So notice that I've given you these values in torr for this problem. Since people probably don't have this memorized, and I can't blame them, 1 atmosphere is equal to 760 torr. Because in one of the problems, you're going to have to convert from torr to atmospheres, just as practice. So I have liquid A and liquid B. So liquid A's vapor pressure at room temperature is 760 torr. Will it boil? Liquid B's vapor pressure at room temperature is 216 torr. Will it boil at that temperature? And then based on the vapor pressures that I have listed for X, Y, and Z, which one has the highest boiling point and which one has the lowest boiling point? So try these problems. We'll go over the answers in about 5 minutes, and I'll see you then. 1 or 2 more minutes, we'll go over the answers. All right, so let's go over the answers here. So remember that if atmospheric pressure equals vapor pressure, boiling occurs. So if I have a liquid who has a vapor pressure of 760 torr at room temperature, then yes, it will boil because the vapor pressure equals atmospheric pressure. Liquid B, on the other hand, does not have enough. So I have 216, but I need 760, so this will not boil. Finally, for these liquids down here, I want to arrange them in order of lowest to highest boiling point. So what we need to do first is convert them all to the same units. So let's do that. So I'm going to convert them to torr. We can do that by doing this. So there are 760 torr in 1 ATM. So we'll go to our calculator and go 0.637 times 760. And we get 484 torr. I don't know what happened there. I just kind of abandoned that. We got our Z. That's already 822 torr. So we would arrange these from highest vapor pressure to lowest pressure, and that would be the lowest temperature at which they boil. So this one would boil not only at this temperature, but a lower temperature. So Z must have the lowest boiling point. And then this is the next highest, so that would be Y. And then this is the lowest vapor pressure, which means it has the highest boiling point. So remember, lower vapor pressure equals higher boiling point. And that's really the takeaway that we need here. All right, we're up for a break, so we're going to take a break. Let me put this here. Let me get the timer on the screen. And no, I don't want to update the timer. Stop asking me. Silly program. Okay, so I'm going to start this. Let's take a 10-minute break. We'll play some more music. Secret Evermore is basically just ambient music for the most part, but there are some tracks in here that aren't, so we'll see if we can get some of those going. Alright, we're back. Let me turn this wind down. Yeah, there's a track on the soundtrack that's just wind. And when I played this game when I was a kid being like, how old would I have been in 1995? 12? I never heard music that was just wind, and that was very interesting to me to play a video game where that's your background music is just wind and like a few instruments. So. There's a whole genre of music out there called ambient, which is just like background noises. Like there's some like cityscapes and other stuff, and like there's a lot of really cool music. So, and I think that this game introduced me to a lot of that. So that's cool. What do we got next? Oh, we have the last part of Chapter 7. This is the most important part, I think. If you're taking biology, which virtually everybody taking this class takes cell bio anyway, it's very important to understand intermolecular forces. The reason behind that is because intermolecular forces are the attractions between ordinary molecules that we would otherwise assume didn't occur. But I did sort of insinuate earlier that these forces exist. And they exist to varying degrees of magnitude. Water, it turns out, has pretty powerful intermolecular forces. You have to heat water up a lot in order to make it boil. Other liquids, we're going to find out, not as strong of an intermolecular forces. So let's talk about what these forces are. So the first thing we want to talk about is what their nature is. So on the screen here, I have HCl covalent bonds. So these are covalent bonds. Covalent bonds are, let me just make that look more like an N. Covalent bonds are strong. Those atoms are held together. That H and that Cl, not going anywhere. Those two are stuck together forever. Not really forever, but by contrast, this right here is an intermolecular force. And intermolecular forces are weak. So if I was going to pull these things apart, so like if I pulled in this direction and then this direction, the thing that is the weakest would break first, and that's this. These numbers just indicate how strong they are. So 16 versus 431. 16 is less, so it's going to break first. Like if you had a piece of string, but it was frayed in one spot and you tugged on both ends, it would snap where the fray occurred. It's the same sort of principle here with these intermolecular forces. If I pull the molecules apart, I'm not going to snap the molecules between the H and the Cl. I'm going to snap them between the molecules where the intermolecular force is what's holding them. Intermolecular forces are going to be drawn with dashed lines because they're not bonds. Bonds are solid lines. Intermolecular forces are dashed lines. And they will just represent an attraction between molecules. Now, if you are pulling your molecules apart linearly like this, obviously you'd snap them in the middle and the force would go away. But we don't really pull molecules. We sort of just heat them so that they can move more quickly. The more movement that molecules have, the less constrained they are by the intermolecular forces. And that's because they have a lot of kinetic energy. Now, I don't really have a great analogy for this, but the analogy I think I would use is that, like, suppose that you're, like, looking for, like, somebody to, like, chat with or go out on a date with at, like, a bar or something. Like, you're looking to meet people. If you're looking at a bar, everybody's sort of stationary and in, like, a certain place. So, like, people might be drinking at the bar itself, or they might be standing against the wall, or maybe they're dancing or whatever. And so you can... an attraction between you and a potential person can form based on the fact that they're just right there, and you can see them, you can talk to them, you can see like what's your favorite thing to do. You can have a conversation basically. So the potential to form an intermolecular attraction exist because you're stationary, you're relatively in the same location. You can create that connection. Now, let's suppose you tried to do the same thing, but you were going to look for people on a highway. So you're standing on the side of the highway and everybody's driving by. Like, there's no chance of you to interact with anybody, right? How would you make friends with somebody driving a semi down the highway? I mean, you wave at them and then they drive right by. Your interaction was very, very brief, so you didn't have a chance to establish this connection here. So with molecules, it's more or less the same principle. If molecules are moving past each other extraordinarily quickly, because we've raised the temperature, they don't form this connection, and thus they don't stick to each other or be attracted to each other. Now, when molecules are stationary in the solid state, these interactions are easy to make. When molecules melt, they start moving in random directions, but they're still at least in close enough proximity to maintain these interactions. Depending on the magnitude of these forces, like we said earlier, that's going to affect the melting and boiling point of our substances. So things with strong interactions will have high melting and boiling points. Things with weak interactions will have lower melting or boiling points. The gas phase we more or less don't care about because at that point the molecules are moving too fast to form these attractions anyway. So here's our example here. We've got hydrochloric acid, HCl. HCl boils at negative 85 degrees Celsius, but water boils at 100 degrees Celsius. Which molecule has the stronger intermolecular forces? You type your answer in the chat, and we'll go over it in about a minute or two. Alright, so like we said, weaker forces mean lower boiling point. So stronger forces must mean higher boiling point. So H2O must have the stronger intermolecular forces because its boiling point is way higher. So let's explore why this is the case. So what forces are present in molecules? So we're gonna outline 3 different intermolecular forces. And what we're going to do is we're going to plot them on a chart of how effective they are. So what we're going to do is we're going to go over here. And we're going to make this chart real quick. So what we're going to do is we're going to say on the y-axis we're going to have strength. And on the x-axis we're going to have how big the molecule is. Generally speaking, if a molecule is really, really small, these forces become more important. But if a molecule is really, really large, then we need a bunch of these molecules that have these forces in order for it to have an effect. And you'll see what I mean in just a moment when we talk about it. So the first force we're going to talk about is called the dipole force. Remember that in chapter 5, we talked about whether a molecule could be polar or nonpolar. So we said, oh, okay, well, let's say I have ammonia here. And we said that the overall polarity of ammonia would be in this direction. So delta minus near the nitrogen and delta positive near the hydrogen sites. Well, if each of these molecules had a dipole like this, all of the delta positive ends would line up in such a way that they would be adjacent to a delta minus on another molecule. Likewise, all of the delta minuses would line up so that they could be adjacent to delta positives. On the right, I have a solid, so example B is a solid. Everything is regularly aligned. On the left would be more of an example of a liquid, where the molecules are loosely arranged around the solution, but they're still oriented in such a way that they are attracted to the opposite charge on neighboring molecules. So these interactions are called dipole-dipole interactions. Dipole-dipole interactions are permanent because dipoles don't go away. If something is polar, it will always have a dipole. So polar molecules have dipole-dipole interactions. Now, we've talked about differences in electronegativity and how you can have stronger polar interactions. And if it gets so strong it becomes ionic. We're going to stick to the polar covalent realm of things because we're working with covalent molecules here. But as you make things become more polar, they have stronger dipole moments. And therefore, the dipole-dipole interactions are more powerful too, and the boiling point of the liquid tends to increase. Now, what does that mean for our little diagram here? So, dipole-dipole interactions are very strong. And so, we're going to put them relatively high on the chart here. So, blue is going to be dipole-dipole interactions. And those are very strong. I'm going to do something sort of like that. Now, as molecules get bigger, you have to have a bigger dipole over the entire molecule in order to maintain the effect. But generally speaking, dipoles form between two atoms forming one bond. So that one bond contributes the polarity of the molecule. If you have like 20 other bonds, the effect becomes a little more limited. All right. And so as a result of that, smaller molecules tend to have more powerful dipole-dipole forces, which is why we drew that on our little chart over here, how we did. Now, if you meet certain requirements, you can get a very special type of dipole-dipole interaction. And those requirements involve hydrogen. And so this is called a hydrogen bond. Importantly, it's called a hydrogen bond, but it's still an intermolecular force. It's not a bond. Because chemists are stupid. And they decided to call this, oh, let's call it a hydrogen bond. That'll just confuse first-year chemists. Yeah, no, it's stupid. It should be a hydrogen interaction, but The premise here is that hydrogen has a delta plus on it. Oxygen, nitrogen, and fluorine have delta minuses. So if I can make this sort of arrangement where I have a delta plus between two delta minuses, I can create a strong interaction. So you need to have a hydrogen. That's the first step in making a hydrogen bond interaction. Then what you need to do is you need to involve it between two atoms that are of these three: nitrogen, oxygen, and fluorine. If you can get your hydrogen to be between those two, and they can be any two, they don't have to be the same, so you can see down here, this is valid. You do not have to have the same of those member of that set of three. But if you can get your hydrogen to be bonded to one of these and then pointed at the electron pair on another one of them, you will create a hydrogen bonding interaction. Hydrogen bonding is basically just a stronger dipole-dipole. Now, do I have the requirements? Yeah, there we go. H is trapped between the two NO or F elements. Now, important requirements for this. I misspelled it. Hold on. So the important requirements for this are that your hydrogen is bonded to either a nitrogen, oxygen, or fluorine, and it's also oriented towards the electron pair on another nitrogen, oxygen, or fluorine. So, for example, if I look at this pair of molecules here, my hydrogen is bonded to a nitrogen and is pointed at the electron pair on another nitrogen. So that checks out. This hydrogen is bonded to an oxygen and pointed at the electron pair on a nitrogen, so that works too. So on and so forth. So if you meet those requirements, you have hydrogen bonded to NO or F, and you're pointing it at an electron pair on another NO or F, you can form a hydrogen bond. Now, like we said, hydrogen bonds are really powerful, so we'll get a new color here. The hydrogen bond is a more effective dipole. In the circled region are our hydrogen bonds, so that's great. All right, what I want you to do is I want you to look at these molecules, which is going to require you to draw the Lewis structure. Drawing the Lewis structure for each of these molecules, tell me which ones can form hydrogen bonds. Now, right away, you should be able to eliminate two of them, and then you don't even have to draw their structure. So that just leaves the last two. I'm going to give you like 3 minutes to fiddle around with this, and then we'll go over the answers together. One more minute, we'll go over the answers. Alright, so, of these two molecules, which two can we eliminate? Well, we need nitrogen, oxygen, and fluorine in order to make hydrogen bonds. So this can't hydrogen bond, and neither can this. Because they just don't have those atoms available, right? There's no H's, there's no N's, O's, or F's in them. I'm going to go over here to this previewer. And we'll put this up on the screen. And I'm going to do this, and just so I don't accidentally erase everything. If I draw the Lewis structure for H2N, and H2, I get something that looks like this, right? And if I do CH3F, that's what I would get. Now, can I take a second copy of each of these molecules and form a hydrogen bond? So if I did this, then I could have a hydrogen bonded to a nitrogen pointing at the electron pair on a nitrogen. So this would make a hydrogen bond. Now, could I do that with, say, this? Is there any orientation that I can make this work? So I have my hydrogen, and it's pointed at the electron pair on a fluorine, but it's not connected to a nitrogen, oxygen, or fluorine. In fact, I have no hydrogens in this molecule that are connected to a nitrogen, oxygen, or fluorine. They're only connected to carbon, so this cannot hydrogen bond. So the correct answer of which molecule can make hydrogen bonds is H2N and H2. Oops, I muted myself, sorry. Here's another example. I want you to draw ammonia and water. So draw an ammonia molecule and a water molecule, and try and make a hydrogen bond out of them. And then draw an HF molecule with an HCl molecule and try and hydrogen bond those together. And tell me which of those situations does form hydrogen bonds and which one doesn't. So I'll give you 2 or 3 minutes for this too. One more minute, we'll go over the answers. All right, let's go over the answers here. So, if we draw water for this example here, and I draw ammonia, I can form a hydrogen bond like this, where I have my hydrogen is bonded to a nitrogen and is pointed at the electron pair on another oxygen. But I could also do this. And you can rotate these however you want to. Where my hydrogen is bonded to an oxygen and is pointed at the electron pair on a nitrogen. Depending on which direction you are bonding, or not direction, but like which atom you are bonding to, in some cases the atom will be the one receiving the hydrogen bond, and in other cases it'll be the one donating. So here, my H is connected to this N, so this would be my hydrogen bond donor, and then this would be my hydrogen bond acceptor. Sometimes molecules are only acceptors of hydrogen bonds. So for example, up here with this fluorine, this is only an H bond acceptor. And that's going to be important to note for chapter 8, which we're going to get to on Wednesday. Sometimes you can only be an H bond acceptor and not an H bond donor. But in some cases, you can be both. So, for instance, here, this nitrogen is also an H bond acceptor. And then the water right here is acting as the H bond donor. For the last example, HF and HCl here, we get stuck on this part. H is not connected to a nitrogen, oxygen, or fluorine, so these two mixed together cannot hydrogen bond. They could form a dipole interaction, but it would not be a hydrogen bond. All right, very good. So let's talk about the last intermolecular force. Oh, here's a graph that talks about how important hydrogen bonding is in terms of like how it affects boiling point. So the only molecule on this diagram that is capable of hydrogen bonding is water. And you can see that boiling point tends to be pretty linear with increasing molar mass, right? So as molecules get bigger, the boiling point slowly climbs upward. But water is a very strange exception. And it's fortunate for that because by virtue of water having such a high boiling point, that means that life can exist in liquid water at a reasonable temperature here. That's pretty confusing. Can you be more specific? So, because water can hydrogen bond here, its boiling point goes way, way up, whereas we would expect it to probably be like down here. Shown here is a diagram of ice where water has crystallized into a particular arrangement. And you could see here that the arrangement of water is shown where here's my bond. Let's pick another color. Okay. There we go. So here's my bond. So H is bonded to an oxygen. And then I have my hydrogen pointed at the electron pair on an oxygen on an adjacent molecule. And I'm sort of doing this in sort of a hexagonal pattern here. So I'm going to just draw these arrows of... Actually, it goes this way. But anyway. It's hard to see these bonds because there's so many superimposed in each other. But I create this sort of like hexagonal arrangement when I do this. And this is the structure that water adopts when it freezes. All right. The last intermolecular force we're going to talk about today in the last 10 minutes we got is what do we do about nonpolar molecules? Do nonpolar molecules interact with each other in any way? And the answer is yes, sort of, which is not a very compelling answer. But let's look at this in a little more detail and see if we can get an idea. I'm going to look at these two atoms of helium. Helium is just 2 protons and 2 electrons, right? My electrons are always attracted to the nucleus of the atom that they are around, but they are attracted to other nuclei too, right? Because opposite charges will attract each other. Positive and negative will draw each other's attention. So what can happen randomly is that if my electrons just happen to be on the same side of the atom, I would create a delta plus, delta minus for my neutral atom. The electrons just happen to be on one side as opposed to the other. If the electrons swing back around, then there are no deltas, and it's just neutral. So we create temporary dipoles. I really wish I could just flip the pen over and erase, but I can't. So temporary dipoles can be formed by the unequal distribution of electrons. Now, this picture's terrible. I wish I could find a better picture of this, but if I have a molecule where my electrons are unevenly distributed, then two sides that have opposite temporary dipoles still attract to each other. And so we get a temporary attraction. And so this temporary attraction is called the London dispersion force. So the London dispersion force is just the result of attractions that happen randomly. Random attractions due to unequal electronic distribution. Dispersion forces are primarily found in molecules that are nonpolar. However, they do exist in all molecules because all matter has electrons, right? However, since they're so weak, we don't care about them in molecules that are polar. We only care about them in molecules that are nonpolar. Now, how do you create a dispersion force, or a London dispersion force, with more reliability? And the answer is that we need to meet a requirement, a polarizability requirement. How can I polarize my electron cloud? And there's two ways to do that. One is that we just need more electrons. The more electrons that are available, the more likely they are to be unevenly distributed. If we're comparing two things with the same number of electrons, we can look at the shape of the molecule, and that'll matter too. So we're going to look at both of these examples here. So for our first example, if I look at xenon versus neon, I'm not going to draw all the electrons on xenon, but here's neon. Neon has like 10 electrons around it. Xenon has like so many electrons. If all it takes is for one electron to be on the wrong side to create a temporary dipole, it's more likely to occur if there are more electrons. So the intermolecular forces between xenon atoms would be stronger than those of neon because they're just more likely to form a London dispersion force. Now, what if I have two molecules with like the same formula or the same number of electrons? Then the shape is going to matter. In these instances, I have two molecules. These are both C5H12. Neopentane looks like this, where all my carbons are in a row. Or I'm sorry, this is N-pentane. H, 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 H. H, 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 H. There we go. Whereas over here, neopentane looks like this. H, H, H. H, H, H. H, H, H. H, H. H. There we go. And if I was to draw like a circle around this, so this would be the shape of the molecule, whereas this would be the shape of this molecule. And you can see that right here. Now, if I take a second molecule and I say, okay, where can the intermolecular forces occur? Well, it can only occur where the molecules meet each other. So that'd be like right here, right? So I could get a delta minus and a delta plus here and form a temporary attraction, but only in this area where they bonk into each other. For N-pentane over here, I have a lot more space for these molecules to interact. So I could form, well, I could form if the pen would stop doing that. We can form several interactions because there's space to do it. Oh, for fuck's sake. Whatever. You get the idea. So all we need are localized uneven distributions of electrons, and we can form these interactions. You could form multiple of them in the molecule, but you do need multiple atoms to do that. And you also need a molecule that's big enough to do that. So as a result, the boiling point of N-pentane should be slightly higher than that of neopentane. And it is by about 25 degrees or so. All right. Now, again, remember, all matter has electrons. So all matter has dispersion forces. But these forces are generally rather weak. But as we saw in that last example there, these forces can become more powerful if more of them are present. And in order for those to become more present, you just need more electrons. So dispersion forces are a bit unique in that regard. They do something like this. That's a little too sudden there. So I want to do that. That's what I was thinking. So at low molar mass, there just aren't enough electrons to get very many intermolecular forces for dispersion. But at high molar mass, if you have tons of electrons, the opportunity for these to occur goes up. Now, we're not going to be looking in this gray area in the middle here, where it's like, oh, which one is more significant? When I give you a question on an exam or a quiz, it's going to say, this molecule is small. What's the most powerful intermolecular force? Well, small molecule, don't pick dispersion. If I say large molecule, then you do pick dispersion. Dispersion is significant when you have larger molecules, and if you have a molecule that is extremely large, it can become dominant. All right. So looking between these two molecules here, CH3F and CH3I, which one has the stronger dipole-dipole forces, and which one has the stronger dispersion forces? Well, looking at iodine here, iodine is not very polar, but it's big. Iodine has a ton of electrons. It's like element 53. So CH3I would have the stronger dispersion forces by far. Fluorine, on the other hand, is very polar, so it would have the stronger dipole-dipole forces significantly. So these are the types of questions that we can now answer. Now, of these two, which has a higher boiling point, that's hard to say. And the answer to that is, well, we'll have to look it up because we don't know if we've crossed the threshold between a small molecule and a large one. Because iodine's pretty big, right? Iodine's molar mass is like 126 on its own. You could get like almost 10 carbons for that. Would a molecule with 10 carbons in it be small or large? Hard to say, right? So, again, we need to have the small versus large molecule label in order to compare them. Oops. So here's our summary. For a small molecule, dipole-dipole forces and hydrogen bonds are more significant. Let's just put this all on the screen here. And then we'll put our little diagram here. If a molecule is very large, dispersion forces take over and eventually become dominant. Your task is going to be to answer questions along the lines of which molecules can perform which interactions. So look to see if a molecule is polar. Look to see if a molecule is nonpolar. Look to see if it has the hydrogen bonding qualifications. Remember that a nonpolar molecule can only do dispersion. A polar molecule that does not meet hydrogen bond requirements can do dipole and dispersion. And if the molecule does meet hydrogen bond requirements, it can do all three. All right. Other questions that you'll be asked will be things, let me put the homework on practice on the board here. Like this. We're not going to do the second question, but I do want you to answer this first question right here. So, of these three, which contain only carbon and hydrogen, which one's a solid, which one's a liquid, and which one's a gas? So, I might ask you about phases. And you know that the stronger the interactions, that will affect what phase the molecule is in. So if the interactions are extremely strong, what phase will the molecule end up as? What if the interactions are extremely weak? What will you get there? So I want you to tell me which of those is the solid, liquid, and gas at room temperature. Type that in the chat. We'll go over the answer, and then we'll call it a day because we're out of time. So I'll give you like 1 minute to try that. All right, so let's go over the answers because we're out of time, really. The molecule with the most molar mass, which is this one, must have the most electrons, and therefore will have the most dispersion forces. So this must be the solid. This has the smallest number of electrons, so it'll have the fewest London dispersion forces. And since we've already eliminated the other options, this one must be the liquid. All right, there's the homework practice for this. This is the end of chapter 6. I'm sorry, it's chapter 7. So, hooray. So that means I will put the quiz up for tonight. That part's not super hooray, but, you know, what can you do? I do want to thank everybody for coming out to the lecture. If you have any questions on Chapter 7, let me know. I'm going to try and finish up all the grading later tonight once I get my other class done. But until then, make sure that you finish the quiz for Chapter 6 that's due tonight and closes tomorrow. And Chapter 7's quiz will be due sometime next week. All right, that's all I got. Have a wonderful evening. Looks like it's going to be sunny later this week, so make sure you get out and enjoy it.